Now, chemistry of elements of second and third transition series. In the previous chapter, we have discussed the position of transition elements in the periodic table. Transition elements belong to D block of the periodic table and are located in between the S block and P block elements in the periodic table. The D block elements involve primarily the filling of T or subshells. The penultimate shell in these elements is being expanded from 8 to 18 electrons by the addition of 10 electrons. We also attempted to define the transition elements as elements which have partially filled T subshells either in the elementary form or in their commonly occurring oxidation states. Strictly speaking, this definition excludes zinc, cadmium, and mercury from the D block elements. This is because these elements do not have partially filled T shell either in the elementary form or in their common oxidation states. The elements of group 12, which are zinc, copper, and cadmium, do not show distinctly the properties of transition elements except for their ability to form coordination complexes with ligands. However, for the sake of continuity and rational classification, the elements of group 12 are included in the D block elements. In this chapter, we intend to explore the chemistry of heavier metals of D block. Example second and third transition series. The heavier metals of the D block are highlighted in figure 2.1. It is interesting to note that like the 3D transition series, the aromatic number of the elements of the second transition series are filled sequentially from 39 to 48. However, there is discontinuity in the atomic numbers between lanthanum and hafnium in the third transition series. In brief, the second and third transition series that involve the filling of 4d and 5d orbitals respectively include the elements with atomic numbers. Second transition series yttrium having atomic number 39 to cadmium having atomic number 48, which are 4d orbitals are gradually filled. Third transition series lanthanum having atomic number 57, hafnium having atomic number 72 to mercury having atomic number 80. In this, 5d orbitals are gradually filled. Electronic configuration of elements of second and third transition series. The general electronic configuration of the elements of second and third transition series can be written as n-1d 1 to 10 ns 1 to 2. When n-1 stands for the penultimate shell, which occupies 1 to 210 electrons in the d subshell, while n stands for the outermost shell that occupies 1 to 2 electrons in the s orbital. Table 2.1 lists the ground state electronic configuration of the elements of the second and third transition series. It is important to mention that the elements of group 7, 8, and 9 are collectively called the platinum group elements. General characteristic of second and third transition series. We have noticed clear period trends down each group in the chemistry of S and P block elements. However, transition elements of second and third transition series shows very strong similarities in their chemistry within a group but show large differences from the elements of first transition series. This similarity is due to the filling of 4f orbitals in the elements that lie between these two rows of elements. Example period 5 and 6. Electrons in these orbitals shield very poorly. The electrons in the outer 6s and 5d orbitals. As a result of poor shielding, the effective nuclear charge decreases with the result that the atomic covalent and ionic radii of the period 6 transition elements are reduced to almost the same as those in the period. Let us discuss the important differences and their causes. First, irregular or anomalous electronic configuration. In the first transition series, the 4s electrons are filled before the 3d electrons in their neutral gaseous atoms. From scandium Onward, the 3D level continues to fill regularly with increasing atomic number. But at chromium, there appears to be an anomaly. In case of chromium, the electrons are so filled that the 4s and 3d orbitals are each half filled. This is due to the extra stability associated with half-filled orbitals. Similarly, at copper, the electronic configuration is anomalous because of extra stability associated with completely filled d orbitals. However, elements of the second and third transition series display much more irregular electronic configurations in addition to half or completely filled d orbitals. The anomalous electronic configuration of the elements are attributed to the several electron-electron repulsions. Second, atomic and ionic radii. The atomic and ionic radii of elements of first transition series are well known. However, the atomic and ionic radii of second and third transition series elements are not known with certainty, with the exception of few elements. As we move down a particular family of the transition metals in the periodic group, there is an increase in size from first to the second transition series, but the size increases from second to the third transition series is negligible. Oxidation state. The oxidation state of the transition metals are higher for the first half of each row than for the later members. Lower oxidation states are found to be more stable in case of first transition series compared to the elements of second and third transition series. The elements of second and third transition series have higher common oxidation numbers than the first transition series. Like the main group elements, the highest oxidation state of transition metal is found in case of oxide. Thus, the highest oxidation state +8 occurs in case of osmium in OSO4. The other compounds that exist in high oxidation state which have no counterparts in the first row V are WCl6, ReF7 and PtF6. It is also interesting to know that superficial similarities in the chemistry of second and third transition series elements exist compared with the elements of first transition series. For example, chromium, molybdenum and W all form the oxides with oxidation number +6. However, chromium 6 oxide is highly oxidizing, whereas molybdenum oxide and W oxide are normal oxides of these metals. Fourth, reactivity. The elements of first transitions are more reactive than the corresponding elements of the second and third transition series. The lanthanide contraction is majorly responsible for the low reactivity of second and third transition series. As an example, gold and platinum are least reactive. The low reactivity is due to the closeness of the valence electrons to the nucleus because of poor screening of 4f electrons. Because of poor screening of 4f electrons, the valence electrons are very tightly bound to the nucleus and are not readily available for chemical reactions. Fifth, stability of the complexes. Transition metals have the ability to form complexes in contrast to S and P block elements. This is due to the small size, highly charged ion, and availability of vacant d orbitals of low energy in case of transition metals. The elements of first transition series form stable complexes with hard donors with nitrogen, oxygen, and fluorine, whereas the elements of second and third transition series form stable complexes with phosphorus, sulfur, and heavier chalcogen donor. Coordination number. The coordination number 6 is commonly found in transition elements, giving an octahedral structure. The coordination number 4 is less common compared to coordination number 6 and gives either squaternion or tetrahedral structure. Complexes with coordination number higher than 6 are less common for the first transition series but are common among early members of the second and third transition series. Legend repulsive interaction become more important for with higher coordination number, and thus it is the smaller legend which allows highest coordination number. There are only few compounds in the which the coordination number is 7. There are three geometric forms known in this case and are shown as monocapra octahedron, pentagonal pyramid, and tetragonally capped trigonal prism. The capped octahedron is shown in by tungsten 2 complex. The capped octahedron is formed by the addition of a seventh atom at the center of any one face of the octahedron. The pentagonal bipyramidal geometry is adopted by the anionic species, that is ZrF7 3 negative, or UF7 3 negative, and UO2 F5 3 negative. The tetragonal capped trigonal prison is adopted by MF7 2 negative, where M is equal to NB or TA. This arrangement is made by putting a seventh atom above the center of one of the rectangular faces of a trigonal prism. Coordination number greater than 7 are also known among the second and third row transition elements. Coordination number 8 is found in the square entry prism as an Na3 Amosian holate and in the dodecahedron as in Bu4N thrice Amosian 8 as shown in figure 2.3a. It is important to note that the solid state structure is sometimes influenced by the counter ions as in case of Na3 Amosian holate and Bu4N whole thrice of MCN whole 8. Coordination number 9 is the limit for covalently bonded d block metal complexes because this represents the full use of the 9 valence electrons. One is 3.5 d orbitals. The anion ReH9 2 negative has a tri-capped trigonal prismatic structure with coordination number 9. Seventh, aqueous chemistry. Elements of the first transition series have a very rich aqueous chemistry. As an example, cobalt 2 forms a variety of tetrahedral and octahedral complexes and display interesting aqueous chemistry. On the other hand, corresponding members of the second and third transition series, RS2 and IR2, do not form such complexes and consequently do not have the aqueous chemistry. However, most of the heavier transition metal, instead of forming simple cationic complex, prefer to form anionic complexes in the form of oxo and halo complexes. The anionic complexes of heavier transition elements have rich aqueous chemistry. Magnetic properties. Compounds with no unpaired electrons are diamagnetic, while those with one or more unpaired electrons are paramagnetic. Most of the transition metals compound are paramagnetic. The diamagnetic behavior arises from the circulation of electron pairs induced by the presence of the applied magnetic field. This charge circulation produces an induced magnetic moment which opposes the applied field and leads to the atom, ion, or molecule being repelled by it. On the other hand, if unpaired electrons are present, the applied field induced a magnetic moment which is aligned with the magnetic field. This effect causes the sample to be attracted in the magnetic field. Paramagnetism results from the interaction of the spin and orbital angular momentum of the electron with the applied magnetic field. If there is no interaction, means coupling between the spin and orbital angular momentum, the magnetic moment mu of s plus L of one atom or ion is related to the total spin quantum number SL to the total angular momentum quantum number L by the expression mu of s plus L is equal to under root g square s of s plus 1 plus L of L plus 1. The magnetic behavior of elements of second and third transition metal ions is more complicated and explained as one has to take into consideration both the spin orbital coupling and the effect of covalent character in metal-agent bonding, where G represents the gyromagnetic ratio. For a free electron, its value is 2.00023 or practically. Therefore, the above equation reduces to mu of s plus L is equal to under root 4 s of s plus 1 plus L of L plus 1. The units of magnetic moment mu of s plus L are Bohr magneton. In cases where the orbital angular momentum contribution is quenched so that 4s of s plus 1 is much greater than L, the expression 2.2 becomes mu of s is equal to under root 4s of s plus 1. This is in fact the spin-only value of magnetic moment. This provides a good approximation of observed magnetic moment mu for first-row transition metal complexes, and it is generally found that mu is less than or equal to mu of S plus L, as shown in table 2.5. In the case of high-spin d ions such as Mn2 positive or Fe3 positive, L is equal to 0, so that no cases mu of OHS is equal to mu S. Thus, from a knowledge of whether the complex is high or low spin, the number of unpaired electrons in a complex can be easily calculated and its magnetic moment values evaluated. Question A. Calculate the magnetic moment mu of S plus L for chromium 3 plus and cobalt 3 plus ions in the absence of magnetic field. B. Calculate the spin-only magnetic moment of Ni2 positive in NiS2 whole 6 2 positive. Answer A. The magnetic moment of the metal ion can be calculated from its S and L values to the equation mu of S plus L is equal to under root 4s of S plus 1 plus L of L plus 1. From the diagram given below, the value of mu of S plus L for different values of S and L can be calculated. That is, for chromium 3 positive, it is 5.1 per magneton, and for cobalt 3 positive, it is 5.47 bm. B. The only spin-only formula of NiS2 whole 6 2 positive contains Ni2 positive. Example, a D8 ion. The octahedral structure shows only 2 unpaired electrons. Therefore, mu s is equal to under root 4s of s plus 1. That is, s is equal to 2 into half is equal to 1, which is equal to under root 4.1 of 1 plus 1 is equal to under 8, which is further equal to 2.84 Bohr magneton. 9. Metal-metal bonding. Metal-metal bonding is very rare in first transition series except in metal carbonyls such as Mn2CO10, Fe2CO9, Fe3CO12, and CO4CO12, and in carboxylate complexes such as chromium 2 acetate, Cr2CS3CO whole 4 H2O whole twice, and in solid nickel dimethyl glyoxime NiDMG whole twice. On the other hand, metal-metal bonding is very common amongst the heavier transition elements of second and third transition series. For example, they form carbonyls with metal-metal bonds similar to those of first transition series. Uh, for example, Ru3CO whole 12, OS3CO whole 12, RH4CO whole 12, and IR4CO whole 12. In addition, it forms RH6CO whole 16. Second, the heavier metals such as MO, Ru, and RH form binuclear carboxylate complexes such as MO2 CH3CO whole 4 H2O whole twice. The halide ions of the type Re2Cl8 2 negative and MO2Cl9 3 negative possess metal-metal bond. A unique feature of a set of 5 elements of the second and third transition series is that these form clusters in which there is extensive metal-metal bonding. The complex cation Nb6Cl12 2 positive and Ta6Cl12 2 positive have unusual structures. Both the cationic species contain 6 metal atoms arranged in a cluster at the corners of an octahedron with 12 prising halogen atoms across the corners. In these clusters, there is an extensive metal-metal bonding. Next, unlike the lower halides of 3D series, the lower halides of molybdenum and W, example MoCl2 and WCl2, exist as hexamers. Example MO6Cl12 and W6Cl12. These parent interesting structures as M6X8 for positive, where M is equal to M and W, X is equal to Cl. 6 metal atoms are arranged in a cluster at the corners of an octahedron with 8 halogen atoms located above each of the 8 faces of the octahedron and bonded to 3 metal atoms as shown in figure. Next, chemistry of ReCl3 is interesting as it exists as a trimer. Example Re3Cl9. It consists of a triangle with three Re atoms with three bridging halogen atoms across the three corners and six halogen atoms that bridge to other Re3Cl9 units, as shown in figure 2.6. Tenth, abundance. All the 10 first row transition elements are widely distributed throughout the Earth's crust and the oceans. Iron is the fourth after oxygen, silicon, and aluminum. Titanium is the ninth, while manganese is the 12th most abundant element by weight in Earth's crust. The remaining transition elements of second and third transition series are very scarce and taken together. These 20 transition elements constitute only 0.025% of Earth's crust in comparison with 6.2% of all the 10 first row transition elements. Molybdenum is a unique element amongst the second and third transition series that plays an important role in human body. Techni- mm, Technetium TC does not occur in nature. Ionization energies. The first ionization energy of an atom is the minimum energy required to convert 1 mole of the gaseous atom into 1 mole of the gaseous unipositive ion. The amount of energy required in this process indicates how strongly the most loosely bound electron is attracted by the nuclear charge. It has been observed that the ease with which an electron can be removed from a transition metal atom is intermediate between those of S and P block elements. The first ionization energy and the successive second and third ionization energies of the transition elements are plotted in figure 2.7. An inspection of the figure 2.7 carefully reveals that the third ionization energies increases more rapidly than the first and second ionization energies. As a result, the transition metals are better indicated by their third ionization energies. The variation of third ionization energies of three sets of transition elements from scandium to zinc, Y to cadmium, and lanthanum to mercury shows that there is a general increase in the ionization energy with a discontinuity after group 7. This discontinuity in the various values corresponds to ionization from a doubly occupied d orbital. The third ionizations from the atom of group 8 to 12 are from doubly occupied d orbitals and are consequently lower because of the increasing repulsion between the paired electrons in the same orbital in the subsequent elements. This discontinuity between manganese and iron is in the first transition series and between technetium and ruthenium in the second transition series reflects additional energy required to break into the half-filled D5 subshells of Mn2 positive and Tc2 positive, which involves the maximum loss of exchange energy. Similarly, in case of europium, the third ionization potential does increase in the third transition series, whereas the 4f7 configuration is reached. Thereafter, it falls back and then increases again on approaching 4f14 configuration at Yb2 positive. In brief, the ionization energies increases irregularly across the three transition series and is less regular in third transition series. Question: why is ZrCl4 the most stable chloride of zirconium when for palladium it is PdCl2? An inspection of the third and higher ionization energies of the d block elements reveal that the ionization energies of the elements increases with the increase in atomic number of the element due to large effective nuclear charge. This causes the third and higher IP of palladium very high, which makes it energetically unfavorable. In addition, towards the end of the transition series, the d orbitals become more core-like. As a result, these are less effective in stabilizing higher oxidation states through covalent contribution of bonding. Taken together, these factors make higher oxidation state less accessible to the right of the d block. In addition, There is greater loss of exchange energy in creating PD4 from PD2 positive than Zn4 positive from Zr2 positive.